Alright, I have the same problem with this section as I did on the last one. I forgot to press record at the beginning of class, or beginning of the section as we covered it in class. So I'm going to go through and get to the point that I picked up and pressed record in class, but I just want to walk through the lecture video for section 1.3. In this section, we're going to be talking about ways that we can develop the differential equations that model phenomenon in the real world. So we actually want to build our differential equations, not just solve arbitrarily chosen differential equations for the sake of solving them, but we want to be able to take a differential equation that has some meaning, some modeling power within the real world to predict what's going to happen in certain scenarios. And so in this section, 1.3, we're going to go through about 4 or 5 different particular models, develop the differential equations, and then we'll come back and use them repeatedly throughout the semester. To begin with, let's just talk a little bit about the process of building a mathematical model in the sense of what goes into the process. What actually are we doing when we go through the steps to create a model? The first thing you always do when you're building a mathematical description of a system of phenomena, which we call a mathematical model, is to identify which variables you want to consider modeling and what variables are inputs to that particular model. So you identify your variables, and choosing which variables to incorporate into your model identifies what's called the level of resolution. So the level of resolution means how granular, how fine-tuned is your model to take into account all possible variables that might have an impact. For example, when we talk about population dynamics in a moment, I'm going to give you a very simple model that only takes into account the population size and the time. I'm not going to have any variables such as a birth rate or a death rate or any components within those populations, perhaps demographics based on different age groups and moving from one age group to another. So more sophisticated models may take into account a whole set of variables, but if you start with the simplest model and then build up from there, you generally can refine by adding variables once you've started with your particular model at a level of resolution that is simple to solve. So we're going to choose several very simplified models in this class, first of all to build up to the types of equations that we would like to solve. But at the same time, we can then take those simplified models and add new variables. We will do that, for example, in our falling objects model, where we have classical Newtonian mechanics being used to model what happens when you drop an object. We will first assume there is only the velocity and the position of that object that is known, a gravitational constant, but we won't allow for any air resistance, for example. And then we'll add to that model what happens if we include air resistance under a certain assumption. So once you identify the variables, then you have to make assumptions. And this is where knowledge of your physical model or your physical phenomena has to come into play. You have to assume the relationship between those variables to build the mathematical relationship between those variables. So these are where you make hypotheses about the system. And you can make these, either conjecture them based on observed data, or you can use your understanding of the system to say, I know that, for example, by Newton's second law, that the forces acting on a system is equivalent to the mass of the object times the acceleration of that object as a result of that force. So that background knowledge is how you inform and build the model. Then one of the final steps is to come back and compare how well does that actually fit with what happens in the real world. Now, on this little cycle that I have drawn down beneath here, you can think of the left-hand side, the 2 boxes on the left, as what's happening in the real world, and on the right-hand side, living in a perfectly aligned mathematical world. Everything in the mathematical world is pure mathematics. We're only going to be solving those variables based on their mathematical relationships and obtaining the solutions. So on the right-hand side, we're living in a perfect mathematical world, and the left-hand side is translating back into the real world. So as we move from the left side to the right side, that's where we're translating a physical phenomenon into a mathematical formulation, and then when you move back to the back from the right to the left-hand side, you're taking your idealized mathematical solution and seeing how well it fits with the real world and what you actually observe. So you start with your assumptions here, and then you express those assumptions in mathematical terms to obtain a mathematical formulation. The mathematical formulation in turn is now a set of equations that you can solve. Now, this actual modeling process is not just true for differential equations. This is what you use in problem solving in general in mathematics. You identify your assumptions, you identify your variables, you form an equation. It may be a differential equation, it may be a simple linear equation, but then you have the mathematical formulation. And having that mathematical formulation, you then solve the model to obtain your solutions. Once you have the solutions, now these again are idealized in the mathematical world. They are the result of your mathematical formulation. So this does not necessarily mean it solves the real world problem. You've only guaranteed at this point that it solves the mathematical formulation. So now you've got to figure out a way to translate it back into the real world. Now that's what I call displaying the model, and that can be anything from graphing the equations to looking at different aspects of your model, plugging in different test cases to see how well that model checks against the real world. So now you compare your model, your mathematical model, to observed real world data. And at that point, inevitably, you will have a difference. And so the variation between the real world and the idealized mathematical world would require that you then refine your model, include either new variables or refine or improve your assumptions, modify your assumptions to get a better predictor of what's happening. And then this becomes a cycle, and you go through the whole process again to continually improve your model. So the first one I want to look at, a particular model in our class is the population dynamics that I alluded to earlier. This is where we're going to model the population as a function of time. We want to know, given a particular population, that means a group of individuals, objects, people, bacteria, any kind of life form or plants or whatever, you're going to model the number of those as a function of time. They're expanding, growing, giving birth, whatever, to a larger population. We want to model that over time. And so our variables for the simplest model that we can come up with is the idea of the population as a function of time. So I'm only going to look at those two variables, and the assumption I'm going to build my model around is that the rate of growth of the population, that is how fast it's changing, is proportional to its size, directly proportional. As the population gets larger, the size grows faster. Okay, that may not be true for all populations. It actually turns out to be a fairly good predictor until you reach a limiting size of what happens when you model the growth of bacteria in a petri dish. Once you reach its carrying capacity, the model breaks. But before that, the model of growth of a bacterial colony is relatively close to this assumption right here, that the rate of growth is proportional to population size. It also has been shown to be true in certain human populations up to a factor, a certain limit on the amount of time over which we model. Now, if we're going to do this, we need to set up an equation, and notice the word rate in this. Rate of growth in this particular problem is the key. That's where you recognize that that's a derivative, right? The rate of change of something is its derivative. By the way, I've written the word Malthusian off to the side there. That just is the name of this particular model. It's a Malthusian model named after a mathematician who first published about it. dp/dt is proportional to the population size. Now that symbol I've written between those two variables, dp/dt and p, is a symbol for is proportional to, which means they grow at the same rate. So if you double one, you double both, right? They're connected in that way. Now, you learn in algebra how to write that as an equation. It turns out when you want to say one variable is proportional to another, the direct proportion equation is dp/dt is equal to some k, a constant of proportionality, times p. But what that equation captures is how fast those two things change are connected to each other in direct proportion. That is, if p doubles, dp/dt doubles. If it's cut in half, its rate is cut in half. But they maintain their proportionality that way through that equation. Okay? So dp dt equals kp. We've actually seen this equation, I think, in your homework when you were asked whether or not you know of any functions that are a derivative of themselves, and then you were asked if there's any function that is a constant multiple, whose derivative is a constant multiple of itself. Okay? So I'm going to stop my video here in my office and combine it, merge it with the video from class. So picking up from here, we're going to continue on in our classroom. All right, so I'm now recording, and we're halfway through population dynamics. Variables population t is time. And this little symbol in between there, it's almost like an alpha, but it's kind of got two little feet off the end of it, like that. That's a symbol that is used to represent proportional to. They grow at the same rate. You double one, you double the other. Okay? But they may not be growing at, like, if you increase one by one, the other one may go up by some factor k. So what you do is you write that as the equation dp dt is equal to kp. And it's not the first time you've seen a differential equation that looks like this. You saw it in your homework problems, I think for 1.1. It said, what function do you know that is a constant multiple, whose derivative is a constant multiple of itself? Did you figure it out? It's like e to the x, but it's got a k in there, right? It's e to the k, t or x or whatever variable, in this case t. So we already know what the solution to this thing is going to look like. It's going to be something of the form e to the kt. But that's what the differential equation now looks like. So that guy right there that I just wrote, dp dt equals kp, that is the differential equation for this Malthusian model. So we're not going to talk about solving it. We just want to be able to write down the equation, know what we're talking about. By the way, in this case, k is positive. Now think about why k has to be positive. So your population p is always going to be a positive number, right? So your population is growing, so the rate of growth, the derivative, needs to be a positive number. You're not talking about in any way is this population declining. So I've not assumed anything in this model of a death rate. I just know that the population is growing proportional to a population size. The larger the population, the faster it grows. The smaller the population, the smaller it grows, but it's always growing in this model. It's one of the flaws of this model, but it does model certain types of populations fairly well for a certain period of time. But k would be positive.
So you didn't use this for like Russia, who has 8,000 people moving out. Okay.
Right. So you wouldn't use that type of model for this because you're not talking about in and out. Although, one of the homework problems talks about if you have a death rate and a birth rate, you can use those in a certain way, and you'll see that when you get to that problem. It basically adjusts this k and considers a case where you could have a negative k, but I want you to look at that and explore that on your own before I give that away to you. Now, radioactive decay turns out to work almost exactly the same way. Whenever you have something that is a radioactive element, such as uranium, plutonium, decaying from one isotope on the periodic table to another isotope, or maybe another isotope of another element, the rate of decay is generally assumed to be proportional to the amount of that substance. So let's model A of t as the, I already answered why, sorry. A of t is the amount of the substance at a given time t. So the rate of decay, how fast that substance is going away, is also going to be the derivative, just like it was for the population. This is dA dt, and it's proportional to the amount of the substance, which is the variable A. So dA dt is proportional to A. I'm really bad at drawing that symbol on the tablet, by the way. That's pretty darn good up there. You should try to model that as best you can. Pay no attention to that one. Okay, so as before, that would mean dA dt is equal to since it's proportional, directly proportional, K times A. But now something happening that's different, right? Because what's happening to the amount of substance? Is it increasing or decreasing? It's decreasing, right? Because it's decaying, so that amount of substance is going away, turning into something else, which we're not measuring. So K would be less than 0. But we typically don't write it this way. We prefer, if we can, to assume all of our constants are positive, unless they're going to be able to be anything. In this case, I don't like assuming that my constant is negative, so what I would do is write it as dA dt is negative Ka, where K now is positive. Because now you can look at that model and see that we're talking about something decreasing because of the negative in it. Now, they're both correct. That's why I put the or in there. But you'll more often see the second differential equation than the first. So if you talk about radioactive decay in any of your homework problems, that's going to be the one that we focus on. Okay. Gladly. By the way, there are a few other models in this section that I'm leaving out. We'll come back to some of them. Some of them we'll just skip over entirely, but you may be interested to see what other kind of simple models we can set up. You're going to have to build a couple of your own from scratch in the homework problems as well, using things like I tell you one's proportional to the other, or I give you some assumptions about the relationships of variables, and you're going to have to come up with your own differential equation based on that. So as we go through this, make sure you're understanding how I'm getting to the model from the assumption. Not necessarily that you agree with or know where the assumptions come from. We're going to take kind of those assumptions for granted in most cases as being established by folks in the field who know the relationship of those variables, for example. Like Newton's law of cooling. This is a classical Newtonian mechanics model, and it doesn't capture things like, what Newton's law of cooling says is if I have a particular object that is at a higher temperature or lower temperature than its surrounding medium, and I place it into that medium. So take a hot ball of nickel and throw it into an ice bath. Okay, or take a human body that is then killed, and how fast does the temperature go to the ambient temperature within the room? I mean, they use that in forensic science to help establish time of death. Or so I'm told by all of the crime shows that I watch on TV. The difference, what we're going to do here is we're going to make an assumption that works for all objects, no matter their size, no matter what. We're going to assume that we know the temperature of the body, we know the temperature of the surrounding room, and then there's a relationship between those two. When truthfully, there are elements about how the distribution of the temperature is throughout the body, the amount of surface area exposed to the surrounding medium, that are taken into account. But I'm going to use a level of resolution that only knows these two variables. That T at T is the temperature of a body, an object at time T. And that whatever medium we throw it into has a given temperature. By the way, the reason I chose the nickel ball that I was talking about is there's a YouTube channel I'm subscribed to on YouTube. That's this guy likes to heat these balls of nickel up to however hot he can get them and then throw them into things, Throw them onto steak. Throw them into a giant block of dry ice or something, And throw it onto an iPhone and see what happens to it. Just video it, It's cool. You should look at Deflator Mouse, right?
There's a channel of a guy who literally only destroys iPhones. Like, he did, brake pads. He did, I have a sledgehammer and 25 iPhones.
Yeah, I mean, You make money doing that because all you got to do is turn on the Google
Money
ads.
back on like every video we did the math.
Yeah. I make a little money off of YouTube. I have a few how-to videos up there, and I make about $100 off Google every 3 months or so.
How many views do you
About 10,000, 20,000. Just
They pay you based off of views?
get?
yep, because you can turn on ads on Google. I mean, I have to report it on my taxes, of course, but I get paid.
Every like, it's supposed to be 1 in 3 videos. The average is about 1 in 5 because of like ad block and stuff, and so you usually get 1 cent per ad view on your video, and so you get like 1 cent per 5 views. So,
Yeah, I'm rolling in the dough. I've made like $300 off YouTube
I
in the
made
last
53
4 or
cents.
5 years or something like that.
Like I made 53 cents off my videos, and
Attaboy.
then somehow Google's like, "You're guilty of fraud," and because I watched my own video like twice, and they were like, "Yeah, you were cheating views," and so now like I can never use Google AdSense again.
Really? Wow.
Yeah, they
You
ban
gotta-
you, and there's
Nothing you can do again.
You're not allowed to watch no videos?
No, I can
Well, I mean, I'm logged in.
I-
When I'm logged in as me and I watch my own videos, they don't count that against it, so that's fine. But
Yeah, I don't know.
you somehow got caught doing something that they didn't like, and you can't make a case for yourself. Once you oppose Google, you lose. So
like,
don't build your life model and your revenue stream for the rest of your life on advertising on Google. That's the worst decision you could ever make.
people do it.
They do it, yeah, but you know, one
Well, the thing is,
flip of a
like,
switch and you're done.
Yeah, a lot of the guys I watch, like, they do sponsorships from other stuff, like Netflix and Audible and all
Yeah.
that. You make your money either way.
So you get up to watch your own videos?
No, I don't know, because they said that I had, like, 50 of my views were from my IP address, and I was like,
It's like Wayland.
it's like, whoa, she's got, like, 10 cents, watch out.
Yep. So, where were we? Oh, we were throwing nickel balls into things and destroying them. Back to Newton's law of cooling. Here's the assumption. The rate at which the temperature of that object or body changes is proportional to the difference between the temperature of the body and the surrounding medium. How far apart the temperatures are, if they're a greater distance, so if one thing is, 1,000 degrees and the other is 0 degrees, it's going to be changing faster than if one is 75 degrees and the other is 74 degrees. Okay?
Are we assuming that the surrounding material temperature does not change?
Exactly. Although, all I have to do to change that is to make this T of M a function of time. And then it becomes a more complicated differential equation to solve. But for now, I'm going to assume that's a constant. Okay, I actually took that problem off of your homework because there was one in your homework where you had to find the function for T sub M, where it was the oscillating temperature due to day-night. So the temperature went up to 72 degrees during the day and down to 32 degrees at night. So you have just a sine wave. So all I had to do, you do have to do sinusoidal curve fitting from trigonometry to find a curve that fits, has a maximum, has a minimum. So all you have to do is use a model, which is like sine of omega t plus b with an a out front. Find the omega, the b, the t, and maybe a shift upwards. Find all the parameters of these so that that sine wave now fits to the oscillation of temperature, and let T of M be that. So you can do that, and it's not that hard. I mean, you just have to go back and remember what all those different parameters mean. This is amplitude, so it's how tall the wave is. This is how wide the wave is. This right here just shifts the wave this way, and this shifts the wave this way. So those 4 parameters are enough to make this roughly fit an oscillating temperature. Okay? But let's assume for now that the temperature is fixed at T sub M. So now what you're going to do is you're going to model exactly what it's got written here. The rate at which the temperature changes is proportional to the difference. So before it was proportional to just the variable of the function, the dependent variable. But now it's going to be proportional to a difference, right? T minus Tm. So dt dt is proportional to T minus Tm. Now you could just as well choose Tm minus T, but you got to make sure you get your constant with the right sign, right? You got to decide, is the temperature going up or is the temperature going down? So when I write this, I'm going to write dt dt, cap T for temperature, little t for time, is equal to some constant of proportionality times T minus Tm. Now when you look at this, if the temperature of the object is higher than the temperature of the medium, what direction is your temperature supposed to be going? Down, okay? So this should then be a negative. Now, if T is bigger than Tm, then this would be positive right here, right? So if I want K to be positive, I'd actually need to put a negative out front. I don't know if I did that. I think I got this backwards. All right, back. Let's fix this, okay? So, that has to have a negative right there in order for, if T minus Tm, the temperature of the body is more than the temperature of the medium, then your temperature is going to be going down, right? So you need that to be negative. So you could write it like that, or you could simply do dt d little t is equal to K, and then do T m minus T, where K is positive. Either one of those forms will work. But you can pay attention. You got to pay attention to, is the sign of your temperature change going in the direct direction? Do you understand what I'm saying? dt dt, if it's positive, the temperature is increasing for the body. If it's negative, it's going down. That's why I had to put that negative over on the first equation that I had. And on the second one, if I just switch it the other way around, if the temperature of the body is less than the surrounding medium, so if this term right here is positive, then the temperature is going to increase until it comes up and approaches that T sub m. So you need the rate of change to be positive. Okay? So that's Newton's law of cooling. This is the model. Now in a given problem, you'll have a T sub m. You'll have an initial condition of what the temperature starts. So you'd have this as an initial value problem. What you don't generally know is the K. The K has to be figured out from the experimental conditions. So in some cases, what they'll tell you is, I know that the rate of change of the temperature when T and Tm are given, and you use that to find your K. But you'll be able to figure that out from the individual problems that you see. Okay, so that's Newton's law of cooling. Make sense? All right, now spread of the disease. I talked about this one a little bit before. What we're going to do is we're going to have a population of healthy or uninfected and infected individuals, and we're going to model the infection spread by the number of interactions between the two populations, X and Y. So let's let X of T be the number that have contracted the disease. Those are the number that are infected with the disease. And we're going to let Y be the number that are uninfected. So you only have two states in this model. So my level of resolution that I've chosen is that there is either you're infected or you're uninfected. When in reality, and given what kind of diseases we could model, there may be cases where you're immune, there may be cases where you're infected, there may be cases where you're a carrier, right, where you are uninfected, but you still can infect somebody else with it. For us, two states, and that's it. And the assumption we're going to make for this simple model is that the rate of people contracting the disease is jointly proportional to X and Y. So this jointly proportional is a way of measuring the interactions between X and Y. So if you held Y fixed and X got larger, then more people are going to contract a disease. If you held X fixed and Y got larger, then more people are going to get the disease. If they both go up, then more people are going to get infected. If they both go down, then fewer people are going to be infected. Okay? So the way that you do a jointly proportional problem is just the product. It's proportional to the product of x and y. So dx dt, which is the rate of people contracting the disease, would be proportional to xy. That's what jointly proportional means, is it's proportional to the product. And since rate of people contracting disease, that's x. So notice this only depends on dx dt. I don't have anything about how fast y is changing, just how fast people are contracting the disease. So that product there models the number of interactions between the two populations. Not an uncommon approach. Am I over time?
Yes.
I'm stopping. 10:41. I got 1 minute I stole from you. I will give it back at some point.
YouTube comments.
Yes, you did. I surrendered that time willingly. I'll come back and finish talking about spread disease next time. 1.2 homework is assigned and is due next time. 1.3 is available. You can start it if you want, but it's not due until next Tuesday. Yes. Get ahead. There'll be plenty of opportunities to get behind. You might as well get ahead while you can.